Okay, yesterday we discussed one important property of Fourier transform, and that was the time shifting property of Fourier transform. Today we shall discuss another property, which is the frequency shifting property of Fourier transform. So property number 3, frequency shifting. Frequency shifting property of Fourier transform. Frequency shifting property of Fourier transform. Okay. And what is the statement? The statement is that if the Fourier transform of small f of t is given by capital F of omega, and I have a real number omega naught. Omega naught belongs to the set of real numbers. Then the Fourier transform of e to the power I times omega naught t f of t. This Fourier transform is given by capital F of omega minus omega naught. So this is the frequency shifting property of Fourier transform. So let us prove this. There is the proof. By definition, we have the Fourier transform of e to the power I omega naught t f of t. It is given by 1 by square root of twice pi integration from minus infinity to plus infinity e to the power I omega naught t f of t e to the power minus I omega t dt. Okay, this is the definition of Fourier transform of this function. Now I can group these two terms together, e to the power I omega naught t and e to the power minus I omega t. So I can group these two terms together. That will give me integration from minus infinity to plus infinity e to the power minus I omega minus omega naught times t f of t dt. Now, if you look at this closely, this is nothing but capital F of omega minus omega naught. Okay, if we had only omega t here, then that would be capital F of omega, and since we have omega minus omega naught here, this is capital F of omega minus omega naught. So we have proved the given property. Okay, so if I take the inverse Fourier transform of both sides, what do I get? So the inverse Fourier transform of capital F of omega minus omega naught, this is equal to, from this we get e to the power I omega naught t f of t. Okay, so this is the frequency shifting property of Fourier transforms. Okay, let us look at one example. So this is example 1. Let us consider a Gaussian pulse, which is given by f of t equal to a e to the power minus t square by twice sigma square. I repeat, this is a Gaussian pulse. Let us find the Fourier transform of this Gaussian pulse. So its Fourier transform would be given by capital F of omega. This is equal to, here a is a constant, so it can be taken outside. a by root twice pi integration from minus infinity to plus infinity e to the power minus t square minus e square by twice sigma square, okay, and e to the power minus I omega t dt. Okay. This integral, we have a general formula. And what is the formula? The formula is that integration from minus infinity to plus infinity e to the power minus alpha t square plus beta t dt. This is equal to root over pi by this alpha, root over pi by alpha e to the power this beta. So beta square by 4 times alpha, 4 alpha, where the real part of alpha is greater than 0. Okay. So this can be derived by converting this to a gamma function. Okay, so this result we can derive by converting this integral to a gamma function. Okay, so let us use this formula here, and that will give us a by root over twice pi. And what is alpha here? Alpha here is 1 by twice sigma square. So we have root over pi divided by alpha, and alpha here is 1 by 2 sigma square. So this is 1 by twice sigma square. And e to the power beta square. What is beta here? Beta here is minus I omega. So this is e to the power minus I omega whole square. So beta square, we have beta square now. Then we have 4 alpha. And this is 4 times. What is alpha here? Alpha here is 1 by twice sigma square. So this is 4 times 1 by twice sigma square. And twice sigma square is a positive quantity, so it satisfies this condition. Okay, so let us simplify this. This is equal to a by root over twice pi. This it becomes root 2 sigma. This root pi and this root pi, they cancel out. So I can remove this pi here. So I have a by root 2, then this root 2, then sigma square root, I get sigma, then this e to the power, this twice sigma square, it will go to the numerator. There's this I minus I square, it will give us a minus 1. So we shall have here minus sigma square omega square by 2. Okay, so if we simplify this further, this root 2 and this root 2, they will cancel out. And what shall we have? We shall have a sigma, then exponent of minus half sigma omega square. Okay, thus we see that the Fourier transform, of a Gaussian function is also a Gaussian function in terms of the frequency. So let us convert it in terms of frequency. So in terms of the frequency, nu defined through we have the angular momentum omega is equal to twice pi times the frequency defined through this, the frequency spectrum. The frequency spectrum is given by f of nu. So we replace omega by nu. This omega, f of omega, we replace it by nu. This is equal to a times sigma. We have a times sigma exponent of minus half sigma omega square. So we have minus half sigma, and omega is given by twice pi nu whole square. So this is equal to a sigma exponent of minus twice pi square sigma square nu square. Okay. So this is the frequency spectrum. So what is the meaning of this? The meaning is that if if I have a Gaussian wave like this, if I have a Gaussian wave pulse given by this formula, then what are the frequencies present in this wave pulse? I repeat, if I have a formula, if I have a Gaussian wave pulse given by this formula, then what are the frequencies which are present in this Gaussian wave pulse, and how much of each frequency is present in that Gaussian wave pulse that is given by this frequency spectrum. It says that the frequency nu is present in that spectrum, and the amplitude of that frequency is given by this expression. Okay, so physically, this pulse is formed by the superposition of a large number of sinusoidal wave pulses. Sorry, sinusoidal waves. I repeat, this wave pulse is formed by the superposition of a large number of sinusoidal waves. And what are the frequencies of the sinusoidal waves? Nu represents the frequency of the sinusoidal wave, and this represents the amplitude of that sinusoidal wave of frequency nu. Okay, so this much amount of that sinusoidal wave with frequency nu is present in that Gaussian pulse. Okay, fine, that is fine. So let us look at another example. Example number 2. Example 2. Let us look at another Gaussian optical pulse. Let us look at a Gaussian optical pulse. Gaussian optical pulse. Consider an optical pulse having a Gaussian envelope. Consider a Gaussian. So consider an optical pulse having a Gaussian envelope given by Et equals a e to the power minus t square by twice sigma square e to the power I omega naught t. Okay, so this is an optical pulse having a Gaussian envelope given by this function. So let us here, what does this represent? The real part of this E. Okay, the real part of this E represents the actual electric field. So the real part of E represents the actual electric field. Okay, so what is the Fourier transform of this Gaussian? I repeat, what is the Fourier transform of this Gaussian optical pulse? That Fourier transform will give us the amount of its frequency or the amplitude of its frequency that is present in the pulse. So the Fourier transform The Fourier transform is given by f of omega. This is equal to a by root over twice pi, integral from minus infinity to plus infinity, e to the power minus t square by twice sigma square, e to the power I omega naught t, e to the power minus I omega t dt. Okay, so this is a by root over twice pi, integration from minus infinity to plus infinity. We can combine these two terms. Okay, so this is e to the power minus t square by twice sigma square, e to the power, I can take minus I common. This will give us omega minus omega naught t gt. Okay, and this we can see from the last example that this will be given by a sigma exponent of minus half sigma square omega minus omega naught whole square. In the last example, we had only e to the power minus I omega t, and here we had only sigma square omega square. Now, since we have omega minus omega naught here, we replace omega by omega minus omega naught in the result that we obtained in the last example. So this is what we have obtained finally for this particular problem. That is, if I have a Gaussian optical wave pulse given by, I repeat, if I have a Gaussian optical pulse given by this expression, then this pulse is formed by the superposition of a large number of sinusoidal waves of various frequencies, and the amplitude of each frequency which is present in that superposition is given by this expression. This is the amplitude of the wave with frequency omega. Okay. So for various values of omega, we have various values of amplitudes. Okay. And this pulse is formed by the superposition of all these sinusoidal waves. Okay. Now let us look at another example, a rectangular pulse. So example 3. That is frequency spectrum of a rectangular pulse. Frequency spectrum of a rectangular pulse. Okay. For a rectangular pulse, we may write f of t, this is equal to a e to the power I omega naught t when modulus of t is less than some tau by 2, and this is equal to 0 when modulus of t is greater than tau by 2. So here tau is the duration of the pulse. Okay, I repeat, tau is the duration of the rectangular pulse. So the Fourier transform of this, the rectangular pulse, so the Fourier transform of ft is given by capital F of omega. This is a by root over twice pi, integration from minus infinity to plus infinity, e to the power I. This a we have taken outside since it is a constant, and we have e to the power I omega naught t. So e to the power I omega naught t. Then by definition, we have e to the power minus I omega t dt. And this is equal to a by root over twice pi integration from minus infinity to plus infinity e to the power. I can combine these two terms minus I omega minus omega naught t dt. Okay, this is fine. Then this integration, it can be solved easily. This is a by root over twice pi. Now, what is the integral of this? The integral of this is given by e to the power minus I omega minus omega naught t divided by the coefficient of t, which is minus I omega minus omega naught. And we insert the limits from minus infinity to plus infinity. Here, I forgot to mention one important thing here. So we divide the interval from minus infinity to plus infinity into three intervals. One from 0 to minus tau by 2, another from minus tau by 2 to plus tau by 2, and third from tau by 2 to infinity. So in the interval 0 to minus tau by 2, the given function is 0. Similarly, in the interval from tau by 2 to, so let me repeat that. In the interval minus infinity to tau by 2, the given function is 0. So the integral of that would be 0. Similarly, in the interval from tau by 2 to infinity, the function is again 0. So that integral will again be 0. So what remains is only integral of this function from minus tau by 2 to plus tau by 2. So this limit, I change it to minus tau by 2 to plus tau by 2. Okay, so I insert the limit from minus tau by 2 to plus tau by 2. So let me insert the limits here, minus tau by 2 plus tau by 2. Okay, then I can simplify this. This is a by root over twice pi. Okay, let me keep the denominator as it is, omega minus omega naught. This numerator, first we insert t equal to tau by 2. So it will be e to the power minus I omega minus omega naught tau by 2 minus e to the power minus I omega minus omega naught minus tau by 2. That minus and minus will cancel. This will become plus. Okay. And here we are missing one minus term. Now, if you look at this closely, this is nothing but 2 times sine omega minus omega naught tau by 2 divided by omega minus omega naught. Okay, so this is nothing but a by root over twice pi. Okay, and I can take 1 by omega minus omega naught outside, 1 by omega minus omega naught outside. So what remains is this divided by minus I. If I divide and multiply by 2, I shall get sine. So twice sine, we have omega minus omega naught times tau by 2. Okay, so this 2 and this root 2, let us simplify it further. So I have capital A root over 2 by pi sine omega minus omega naught tau by 2 divided by this omega minus omega naught. Okay, so this is the Fourier transform of a given rectangular wave pulse, which is given by this function. Okay, and this shows that this rectangular pulse is again formed by the superposition of a large number of sinusoidal waves, and the amplitude of the wave with frequency omega is given by this. Okay, I repeat, the amplitude of the wave with frequency omega in dead square position is given by this expression. Okay. And for omega naught tau much greater than 1, if this omega naught times tau is much greater than 1, then f of omega is a very sharply peaked function around omega equal to omega naught. Okay, so if this omega naught tau is much greater than 1, this f of that is, this function is a very sharply peaked function around the omega naught. Okay, so that is fine.